Welcome to this installment of Epidemiology of Everyday Life Lessons. In this installment, we will talk about how to get probabilities from a linear regression model with a categorical predictor. As I mentioned in previous installments, this is our simple regression model. Y hat on the left side represents our predicted value. This is our best guess of the outcome. We use two parameters to predict the value, beta naught and beta 1. Notice that beta 1 is multiplied by xi. The subscript I below the x means that the value can change for each observation in our dataset. It doesn't have to change, but it can. Notice on the very far right you see ei tilde n with 0 and sigma in parentheses. It's all very confusing. But what we do is we read this where ei is distributed normally with a mean of 0 and a standard deviation of sigma. That tells us how well our mean measures our outcomes. Two elements in that jump out. First, the average error equals 0. This is just like the mean. In fact, regressions are just complicated means. The data follow a normal, aka Gaussian, distribution. That means that we can use the same methods to predict the probability of particular events occurring that we did with the mean. So let's move to an example, and let's use the example of sleep. Our model predicts how much sleep I predict to have on a given night. I know that my sleep patterns differ on weekdays and on weekends. On weeknights, I average about 6.5 hours of sleep. On weekends, I average about 8.5 hours of sleep. See if you can take a second to write the model that represents my predicted sleep. If you're having some trouble, xi equals whether the day is a weekend or not. And that's it. Our model is y hat equals 6.5 plus 2xi plus ei. And I also calculated when I took these measurements that I had a standard deviation that equals 45 minutes of sleep. Now I can rewrite the equation to represent the model of my sleep in its entirety. Beta naught represents the average sleep that I get on a day when xi equals 0. Beta 1, on the other hand, represents the difference in the average sleep between weekends, when xi equals 1, and weekdays, when xi equals 0. Now we can answer a question like this. What is the probability that I sleep more than 8 hours on a weekend? Let's start by looking at the graph of the probability of getting different hours of sleep. But this looks odd. It looks like a double-humped camel rather than the single-humped camel Gaussian distribution that we're used to looking at. And that's a problem because it means our errors are different at different parts of the distribution. Well, it turns out that's because we're looking at a mixture of two normal distributions rather than a single normal distribution. The peach one that measures the distribution on weekdays and the blue one that measures the distribution on weekends. And since there are more weeknights than weekends, we are more likely to experience the peach distribution than the blue distribution, which is why the peach distribution is larger than the blue distribution. But regardless of where this distribution comes from with our double-humped camel, we still end up with a distribution that doesn't resemble a Gaussian distribution, which will cause us problems. But what if we shifted the blue distribution 2 hours to the left? We end up with overlapping distributions. But how do we know to move it 2 hours? Well, we know from our model that I get 2 more hours of sleep on the weekend. So the weekend mean is 2 hours greater than the weeknight mean. The blue distribution was therefore 2 hours greater than the peach distribution. Both, however, have standard deviations of 45 minutes. Shifting the blue distribution to the left accounts for the difference we already predict in our model. And when we do, we see that our errors form a single Gaussian distribution, just like our errors from the mean. Now we can use the same principles that we have been applying to the error of means to the error of the regression to calculate probabilities of certain events. And since we are working with errors, we will now measure the x-axis in terms of hours away from the mean, rather than the number of hours themselves. And now we can begin to solve our question. Our first step involves predicting the number of hours of sleep. We write out our model, and then we fill in the values. We are setting our critical value equal to 8. So y hat star equals 8. And we were measuring a weekend, therefore we set xi equal to 1. Our predicted value for the weekend equals 8.5, which, remember, is the average sleep that I get on the weekend, resulting in an error of negative half an hour. In order to find the probability now, we need to convert that value to z-scores. We can do that by dividing the number of hours per standard deviation to get the error expressed in units of standard deviations, which is what z-scores are measured in. Therefore, we want to figure out the probability that we sleep more than negative 0.67 standard deviations from our predicted value. To get the value, we will use p-norm in R. I tend to remember to use p-norm because p means that the function returns a probability. So at the R prompt, we type p-norm and then parentheses negative 0.67, and R tells us that the area covers 24% of the graph. But wait, I should get more than 8 hours of sleep on average, considering the average is 8.5 hours of sleep, so 24% doesn't seem correct. Well, that's because 24% represents the left tail of the distribution. We need to get the complement, so we subtract the probability of being on the left tail from 1 to get the probability of being on the right tail. When we do that, we get 0.758. So, to answer our question, what is the probability that I sleep more than 8 hours on a weekend? 76% based on my model. So, to review, we use this type of simple regression with a single variable that can take on two values to account for differences between groups, in this case the group of weeknights and the group of weekends. We assume, however, that the errors for both groups follow the same distribution. And finally, we can then use the same methods that we used with the mean to predict probabilities from a normal or Gaussian distribution. So that's it. You can see that the relationship between means and regressions is very close and that we use many of the same methods to calculate the probabilities. So that's it for this installment of Epidemiology of Everyday Life Lessons. I hope to see you again on a future installment.